Greetings and welcome to another installment of Quantities. This is 11 in our basic application series. This time around, we're going to close out our mini-series on continuous quantities here. If you are a Quantities power user, you will have noticed the capital I down there in the title section, and you will know that I stands for intermediate. This is the first Quantities installment classified as intermediate. To close out our discussion on continuous quantities, we're going to ramp up to some pretty geeky stuff here. So to keep track of the nerd factor for the first time ever here on Quantities, we're going to break out the official Quantities nerdmometer right there. Now I want to stress what we're looking at here is the official Quantities nerdmometer. Okay, this is not one of those cheap knockoffs that we've all been hearing about. Okay, in the previous edition, we looked at a couple continuous distributions, including a normal or a Gaussian distribution here. And in both, labeling the ordinate, that is the y-axis here, we have this dimension called density. So what's density? If you've ever taken a physics class, you will have learned that physicists are absolutely cuckoo for Cocoa Puffs about units. Units, as well they should be. Units are absolutely key. In stats, not so much really, and this is somewhat unfortunate, I think. But if we're comfortable with units, and we should be, then this so-called density dimension is easy to deal with. It turns out that density takes on units that are the inverse of the unit or units of the quantity or random variable. So for example, if our quantity is in units, say, meters, then its density will be in units 1 over meters or units per meter. If our quantity is in units meters per second, like a velocity, then its density will be in units seconds per meter. If you happen to get the reference there in the third example, tip my hat to you. Anyway, we can think of a quantity's density as being a rate with respect to the units of the quantity, a rate with respect to the units of the quantity. If you're curious about how we know this, you're encouraged to leave a comment down there. Ramping up the nerd factor here. Strictly speaking, continuous distributions are usually thought of as being theoretical, and I mean this in two different ways. The first, I think, is pretty obvious. A continuous variable is not empirical, meaning that it cannot present itself to us through a collection of data points, and this is obvious because there is no such thing, at least that I'm aware of, as an infinitely large data set. The second reasoning here is sort of out on the hinterlands of scientific thinking, and that is that there is a question if anything in nature truly possesses a measure that is continuous. Okay, so the takeaway here is that continuous variables and their distributions are idealizations, and they're idealizations that can be used to approximate or model a distribution of an attribute within some population. And by the way, this can also be true of many discrete distributions in quantities, escalating the nerd factor here even more. In part 2 of this mini-series, we encountered our buds, the rational numbers. We learned that the set of rational numbers is dense or densely ordered. Any interval of rational numbers with positive length here is also dense. As such collections contain an infinite number of elements. Rational numbers have a certain intuitive appeal, there's no question. Anytime we write a number in decimal form, we are representing a rational number. Anytime a computer stores a numeric value in memory, it is representing a rational number. Because the set of rational numbers is dense, it is also regarded as continuous. It's a continuous set. It turns out, however, that because the rationals are so-called disconnected almost everywhere, with respect to the reals, the rational numbers do not define a so-called continuum. The set of real numbers, on the other hand, includes all the rationals along with all the irrational numbers. Numbers like the square root of 2, pi, the base of the natural logarithm called e. Just like the rational numbers, now the real numbers are dense. Okay, they're densely ordered, dense in itself. But unlike the rational numbers, however, because the set of real numbers is everywhere connected, it does define a so-called continuum. In fact, the real numbers are sometimes simply referred to as the continuum. So this is important. Traditionally, when we encounter so-called continuous distributions or their associated continuous variables, we assume that the domain is the real numbers. That is the union of all the rational numbers and all the irrational numbers, or some subset that is closed within it. And when I say traditionally, I mean like deeply rooted in the theory of calculus and the theory of measure theory and set theory. And when I say deeply rooted, I mean like many decades and even centuries worth of roots. As a result, probability density functions are most always defined over the real numbers. Now, if this gives you a feeling that your intuition has been wrinkled, you are not completely unjustified. We just got done appreciating that not only is a set of rational numbers infinite, but any interval of positive length contains an infinite number of values. We just talked about that. The set is continuous. However, common convention is to represent the distribution of rational variables as a probability mass function, which is discrete. So for this reason, and also considering that the domain of integers is infinite, an implication of this is that there may be occasions where it may be very challenging to graphically represent a quantities distribution in a satisfactory way. Okay, so that's not a huge surprise, I don't think. The other consideration, I think, is much more nuanced here. Since the rationals are a continuous set, we might naturally be tempted to express a distribution that's over the rationals as a probability density function. However, like we just said, the usual machinery of calculus, that is finding the area of a distribution by integration, doesn't play out very nicely for us. So I'm going to suggest that there are two cases where we may want or need to have a domain defined over only the rational numbers. So the first is that we may want to define an attribute that quite simply is a ratio of integers. So I'll give you an example. Like, for example, suppose that our population is all the regular season completed NBA games over the last 10 seasons. We may want to create an attribute that is a ratio, say, of visitor total points divided by home team total points. Not at all a problem. The other simply is maybe we just don't like irrational numbers. Maybe in childhood we had a bad experience. Maybe we got beat up by a bunch of irrational numbers on the playground and we just don't like them. Completely our prerogative. In the first case, to say this as simply as possible, it turns out that the mass function may not possess the smoothness we would like to see or expect in a density function. In the second case, we have two options. The first and best option is to simply forgive the irrational numbers and model our attribute domain as a continuum of the real numbers. Otherwise, really constructing measures over countable spaces is really not an issue. It's pretty trivial. Oh, I lost track of the official Quantslav nerdmometer. Think it's going to blow. Run for your lives. We're all goners. The end of humanity. I'm just messing with y'all. If you made it through our Continuous Quantities mini-series, you are a true Slav Nation master. Nice job. And that's it. That's going to do it this time around. Thank you very much for tuning in, and don't forget to stay tuned for more Quantslav.